The first speaker today is Abubakir Dzhuraev, and he is an expert in differential equations, dynamical system. Sorry about that. He is an expert in differential equations, dynamical systems, and optimal control. And he is going to talk on development of a singular perturbation theory for a linear ordinary differential equations. Please enjoy.
Good morning, ladies and gentlemen. Topic of my report, development of singular perturbation theory of four linear ordinary differential equations. We consider a linear singularly perturbed equation 1. Epsilon tends to plus 0. Here, A from T is a square matrix of order n equal to 3 in order. For convenience of presentation, we consider the case then n equal 2. Let lambda 1 and lambda 2 be constant eigenvalues of the square matrix A from T. Then there are only 7 classical cases for equation 1. 1. Matrix minus 1, 0, 0, minus 2. Lambda 1 equal minus 1, lambda 2 equal minus 2. Matrix 1 is diagonal. Eigenvalues are less than 0. The asymptotic solution of equation 1 depends on the exponential functions. And an initial value problem is possible. This direction was studied by Tikhonov, Lomov, and others. 2. Minus 1, 1, 0, 1. Mean minus 1. Lambda 1 equal lambda 2 equal minus 1. Matrix 2 has a Jordan structure, has one double eigenvalue less than 0. The asymptotic solution of equation 1 depends on the exponential function, and an initial value problem is posed. This direction was studied by Tamarkin, Trzhinsky, Lomov, Eliseev, and others. 3. Matrix I 0, 0, 2I. Lambda 1 equal I, lambda 2 equal 2I. Matrix 3 is diagonal with purely imaginary eigenvalues. The asymptotic solution of equation 1 depends on the trigonometric functions, cosinus, and it is possible to pose both the initial value and the boundary value problems. This direction was studied by Bogolyubov, Mitropolsky, and others. 4. Matrix 1, 0, 0, 2. Lambda 1 equal 1, lambda 2 equal 2. Matrix 4 is diagonal. The eigenvalues are greater than 0. The asymptotic solution of equation 1 depends on the exponential functions, and it is impossible to pose either the initial or the boundary value problem. 5. Matrix 1, 1, 0, 1. Lambda 1 equal lambda 2 equal 1. Matrix 5 of Jordan structure has one double eigenvalue greater than 0, the asymptotic solution of equation 1 depends on the exponential function, and it is impossible to pose either the initial or the boundary value problem. 6. Matrix minus 1, 0, 0, 1, lambda 1 equal minus 1, lambda 2 equal 1. Matrix 6 is diagonal. The eigenvalues have different signs. The asymptotic solution of equation 1 depends on the exponential functions, and a boundary value problem is posed. This direction was studied by Vasilyeva and others. 7. Matrix I1, 0, I, lambda 1 equal lambda 2 equal I. The matrix 7 of the Jordan structure has one double purely imaginary eigenvalue. The seventh direction, the eigenvalues of the limiting operator are purely imaginary and have multiplicity, has been addressed in my work using a specialized method of asymptotic integration for boundary value problems. This latter mathematical approach depends on the exponential functions, has made it possible to completely resolve all 7 directions of the general theory of singularly perturbed linear ordinary differential equations. The 7 directions. Consider a system of n singularly perturbed ordinary differential equations with a multiple spectrum in the case of a matrix of unicellular Jordan structures 1 at epsilon tends to plus 0 with boundary condition 2. To study problem 1, 2 for sufficiently small epsilon, we require the following conditions to be met. Condition 1, A from T, H from T. Condition 2, the spectrum lambda k of the matrix A from T for each satisfies the requirements on the segment 0, 1, conditions 1, 2, 3. Condition 3. The matrix has a Jordan chain of vectors of length n from A, phi. The canonical structure of the matrix A from T equal lambda from T E plus T from T. The T from T is the proper nilpotent of the matrix A from T. The derivatives of the eigenvector and adjoint vectors are decomposed according to the base phi 1, phi n, and sigma. We will make up a structural matrix from the decomposition coefficients B. This C1n from T corner element. And we will require what for the corner element C1T from T. Dzhuraev's condition was fulfilled for condition less than 0 from k equal 1 and n 0, greater than 0, k equal n 0 plus 1, m 0 plus 2, and n. There, C is the primitive nth root of unity. For asymptotic integration of the boundary value problem 1, 2, we introduce additional independent variables according to the formulas 3, 4 from tau k, tau k. Tau k from 0 to t, tau k from 1 to t. There the functions g, I, k from t are determined from the iterative equations sigma. Their coefficients p, m, j, k are calculated using the formulas 5. G, j, k from t for s equal 0, we obtain p n n k plus c 1 n from t equal 0. And hence we have g1 k from t equal this c1 n from t corner element. There is C is the primitive nth root of unity. Introducing the notation tau and C, instead of the discrete dose solution y from t epsilon of problem 1, 2, we will study a new extended function u such that we select 2 points m0 and m1 and define the function and pose the following new extended boundary value problem. This 7, 8 as epsilon tends to plus 0. Science problem 7, 8 is regular in epsilon as epsilon tends to plus 0, then naturally we will define its solution in the form of a series 9 for u, with coefficients from the space of non-resonant solutions u. In the space of non-resonant solutions u, we will define the following operators 10 from L0, G0, G. We use operators 10 and rewrite the extended boundary value problem 7, 8 in the form 11, 12 for L0 and G. We substitute the power series 9 into the boundary value problem 11, 12 and obtain the following iteration problems for determining the coefficients us from t tau of the series 9. 13, 14, 15 formulas. the space conjugate to the space we can be identified this the space of non-resonant solutions. We introduce the scalar product of the elements U by the elements V using the formula from U EV. Lemma. The conjugate matrix has a Jordan chain of conjugate vectors. The systems of vectors and conjugate vectors can be coordinated so that 16. The operator L0 is called basic. Using condition free for the basic operator L0, we obtain the following relations. 17 theorems. Let use consider iterative problems 13 and 15. The following theorems 1 and 2 are valid for the problems. Theorem 1. Let the equation 18 be given in the space U. The L0 is the main operator defined in 10. F from T tau and condition 1, 2, 3 are satisfied. Then for the solubility of equation 18 in the space U, it is necessary and sufficient what the right hand side F from T tau be orthogonal, identically with respect to segment 0, 1 to the kernel of the adjoint operator L0. Theorem 2. Let a boundary value problem be given in the space U, 19 and 20. The L0G are the operators defined in 10. Let conditions 1, 3 be satisfied and the functions G, J, K from T are roots of equations 5 identically with respect to segment 0, 1. Then, first, there exists a general solution to the system of equations 21 and 22 with arbitrary constants. Second, if conditions 23 and 24 are satisfied, then a boundary value problem 19 and 20 has only a zero solution. Based on theorems 1 and 2, we will solve all iterative problems 14, 15 sequentially. This way we will find all the coefficients of the asymptote series 9. Let us formulate the main result for the boundary value problem 1 and 2 in the form of a theorem. Theorem 3. Let conditions 1, 3 be satisfied for a boundary value problem 1 and 2, and let the solutions of boundary value problems 11, 20, we define it in the form of a power series 9 from the space U. Then, when condition 4 is fully filled, the narrowing of the series 9 for tau and epsilon tends to plus 0 is an asymptotic series for solving boundary value problem 1, 2. Thanks.
Thank you. Are there any questions from the audience?
Eigenvalues are T independent, right? So T can be gauged out by diagonalizing the matrix. Is that true?
T. Я понял. Я предполагал постоянными собственные значения, но они и для переменных тоже можно использовать. Просто я указал постоянные. А для любых t от 0 до единства можно диагонализировать в этих случаях. Да, от t зависит.
Can you translate it in English, please? Can you ask the question and say the answer in English?
So the answer is that so the eigenvalues can depend on T as well.
Thank you. Any other questions? Yeah. Okay, if there's no questions, let's thank the speaker again.